Now we have Tomasz Bigaj going to talk about consistent histories and medieval worlds.
Okay, thank you. So first of all, let me thank the organizers and Lev in particular for putting up this wonderful conference. I've learned a lot, I've enjoyed a lot, especially yesterday's trip to Jerusalem. And of course, the time has come to pay my dues. So for the topic of my talk, I have selected a comparison between two interpretations. One is perhaps less popular here, the consistent histories approach, and of course the many word interpretation. And I would like to point out that in spite of some formal similarities, these are two distinct interpretations, and I will try to make them a little bit closer to each other. So I will give my own proposal of how to make the consistent histories a little bit more in line with the many words approach. And I really look forward to hearing your comments to that. And if you think that it doesn't make much sense, then I'll accept that. Okay, so let me start with a couple of words regarding the consistent histories approach. I presume that many people in the audience know much more about this interpretation than myself, so I'll be very brief, and I apologize if I say something quite obvious. Okay, so let's start with the notion of a framework. And this is a notion which involves a projective decomposition of the identity operator within a particular Hilbert space, and formally it can be written down like that. And basically the idea is, the idea underlying the consistent histories approach is that in order to perform any sort of quantum reasoning involving probabilities, etc., you have to select implicitly, or explicitly better, you have to select a particular framework in order to do your reasoning. And there's this single framework rule, which I will talk about more later, which basically prescribes that you cannot mix up two distinct frameworks, okay, due to the problem of incompatibility. Okay, so the framework can be considered at a particular moment of time, but it's much more, of course, interesting if you consider a sequence of moments, which, of course, gives rise to some evolution and histories. And here is the notion of a history and families of histories. Generally, I mean, we start with a Hilbert space, which is, formally speaking, a tensor product of several Hilbert spaces, each of which Hilbert spaces of these Hilbert spaces represents a particular state of the system. I mean, can represent state of the system, housed state of the system at a particular moment of time. So you take a sequence of several like discrete moments, and you consider like what's going on with a particular quantum system. And a given history consists of the tensor product of several projection operators, each of which belongs to a particular Hilbert space taken at a given moment of time. So you have moment t0, t1, up to a certain number tk. And the family of elementary histories, again, creates this projective decomposition of the identity operator. And of course, based on this, you can also add some more histories by taking some linear combinations of these elementary histories. But I will, of course, stick to the elementary histories, which are sometimes also called sample space. Okay. So, and of course, the whole physics starts when you introduce probability functions. So you can define a classical probability function, which is defined on this Boolean algebra based on a given family of histories in a standard sort of way. And finally, and how can you do that? I mean, how can you, assign the probability function? I mean, you can do it if you have a well-defined dynamics, and this is standardly represented by a unitary evolution operator, which takes you from a particular moment of time t sub j to t sub I in the usual standard way. And that way you can define a well-known thing which is called a chain operator, and this chain operator is best read from right to left, as it should be. So you start with the initial state, sort of initial point of time, then you apply the first unitary operator, the second, and so on up until you get to the final projection operator. And given that you have these chain operators, you can define an inner product on these chain operators, again in a standard way using the trace operation. And that way you can assign probabilities to any history by taking the inner product of the chain operator corresponding to a particular history with itself. And of course, this also brings us to a very important consistency condition from which the name consistent histories approach derives. And the consistency condition is that the oh, sorry, there's a mistake here. I realize it should be alpha and beta. So, of course, the inner product of the chain operator for the history y alpha and y beta equals 0 for alpha distinct from beta. Sorry about this mistake. Okay, so this is this gives rise. So only consistent families of histories are such that satisfy this condition. Now it may be worth mentioning in passing that consistency, the consistency of a particular family depends on the underlying dynamics. So it's not so that if you are given a family, it doesn't necessarily, I mean, you don't know whether it's consistent or not. You have to add the dynamics. Okay, so it's very possible, and there are some simple examples of that you have one and the same family which is consistent under one dynamics and it's not consistent under another dynamics, okay? All right, now let me just give you two very special and sort of standard examples of families of histories. One example is histories with a fixed initial state, which is rather a natural way of looking at an evolution of a quantum system. So I start with a pure state psi 0 at the moment of time t0. And then you consider any sort of projector operators, projection operators, projectors, you really wish. So there's no limitation here, as long as everything is consistent. Plus, of course, in order to have you have to complement this, plus the history which starts with the complement of the initial state. This is purely because we want to have the condition of the projective decomposition of the unity operator satisfied. It doesn't play much of a role, the other history. We are focused on the histories of the first kind. Okay, so this is the first type. Now the second type, this is kind of like a special type of these histories with the fixed initial state. These are unitary histories, very important type. And of course, this consists of, this unitary histories consist of states such that each subsequent state is obtained by applying the evolution operator T to the previous one. So this is what we are typically assuming, considering the evolution of a quantum system. Okay, you start with the initial state and then you evolve it according to a particular unitary operator, evolution operator. Okay, and of course the remaining complementing histories. Of course, a special way about unitary histories is that they receive only probabilities 1 or 0. So one is the first one is 1, because this is exactly what is predicted by applying the dynamics, and all the other complementary histories are they receive probabilities 0. So so this is essentially like the unitary history is something that goes well with the Everettian interpretations with Everettian. The Everett interpretation sort of assumes that that's what, I mean, there's this unitary wave, unitary wave function, which sort of devolves in time. But according to the consistent histories approach, this is only one of many. There's nothing special or privileged regarding this particular history. I mean, you can choose any history or any family of histories you want in order to describe whatever you want to describe. Probabilities of some particular outcomes or whatever. So, so there are some general rules which govern the use of frameworks, or in this particular case of families of histories. And these rules, incidentally, my presentation is based on Robert Griffiths' both book and in his later publications papers. So this is Robert Griffiths is one of the founders of this particular interpretation of quantum mechanics. So Griffiths lists several rules regarding how we should use the frameworks, okay? And the first first rule is the principle of liberty. So we can choose whatever framework you want. We are not restricted by any high-level considerations, okay? You can choose, you know, as long as you choose a framework that's consistent, you can do it. The second, which kind of they go hand in hand, the principle of equality. So, like I said, like there's no privileged frame of not of reference. There's no privileged framework. There's no privileged family of histories. Okay, that's the second rule. I mean, the third rule he states is the principle of utility, which sort of I wouldn't say that it goes against the first two, but it's sort of like weakens a little bit. I mean, even though all these frameworks that we can select are equal, but for purely pragmatical purposes, you may want to use one rather than the other. So the principle of utility is use the one that fits best what you want to say. So if you're considering like the probability of particular, I will give you later an example in a moment, an example which will explain it perhaps better. But if you want to consider particular probabilities of particular outcomes, so you should choose the framework that gives you a specific, a definite answer to your question. Okay, so that's kind of like the essence of the principle of utility. And there's the principle of incompatibility, which is associated with this rule that I mentioned at the beginning, the rule of the single framework rule, which states that distinct frameworks are incompatible because they consist of sort of like incompatible decompositions of the identity operator. So therefore, they should not be mixed. I mean, you cannot put them together. You cannot consider the incompatible observables at the same time, or incompatible projection operators at the same time. Okay, now the main question for a philosopher, as I'm a philosopher, for a philosopher the main question is like, how does this interpretation relate to the objective reality that we're supposed to describe here? And here Griffiths gives some sort of cryptic remarks, to be honest. And for instance, one of many remarks that he makes is given here. The physicist's liberty to choose different frameworks should not be thought of as in any way influencing reality. So it's kind of like, here is this reality, and we somehow choose some aspects, okay, of it. I mean, he uses several analogies, which almost each analogy that he uses in his works like ends like with a commentary. But it's not a full analogy, which kind of like defeats the purpose. So like he gives the analogy of the Mount Everest that you look from both sides, and then he says like, yeah, but you can combine these two descriptions, but in quantum mechanics you can't. so all these analogies work only up to a certain point. Okay, so that's a little bit frustrating. Okay, so my impression is that all these rules have a clear epistemological and I would say even pragmatical bias. I mean, essentially, they give you a prescription what you should and should not do rather than a description of what is really there, out there. And I take it that for a realist theory, we should, first of all, from a realist theory, we should demand that, precisely that. I mean, that should tell us what the world is like rather than what we should or should not do with our sort of descriptions of the world, okay? So here is the question, is this approach even realist? And I think David Wallace in his general paper about philosophy of quantum mechanics from 2008, he actually posed this question that most probably it's not a realist interpretation, it's sort of like it gives you some sort of a set of rules, you know, how to reason in quantum mechanics, but it doesn't tell you exactly what the world is. So I'm kind of trying to overcome this obstacle. So my possible remedy that comes to my mind is to interpret frameworks somehow objectively as referring to some sort of subject-independent realities. And what could these realities be? Of course, everybody knows, possible worlds. So let's just try to interpret the consistent histories approach as if all these families of histories, consistent families of histories, represented some distinct worlds, okay? But of course, it's a little bit tricky. It is tricky because, you know, we are used to this picture of distinct worlds which really differ with respect to things like, in one word you have spin up, in the other word you have spin down. So there's some sort of, I mean, they differ with respect to the position, for instance, possession of specific values of observables. But that's not the case when you apply this notion to frameworks, okay? This, it can be proven relatively easily that if one framework, an observable, receives a definite value A, there cannot be an alternative framework in which the same observable receives a different value B, okay? It may happen that in an alternative framework you cannot associate with a particular observable any definitive value, but it's not the case that you will assign a different value, okay? So in a sense, these worlds, they're distinct, but they're not separate. And I know that at this point I cannot explain it any further. I mean, there's some sort of, there is something to it that they kind of represent different, like different sides of the one and the same reality, but in a sort of objective way. I can't spell it out any better at this point. That's probably the best I can do. So, like I said, frameworks are incompatible, but they're not mutually exclusive. Okay, that's the point. However, of course, we have to keep in mind that within a particular family of history, there's this more like fine-grained distinction between particular histories. Okay, and some of these histories receive a positive value, a probability value. Some of these receive 0. And in some cases, like in the case of unitary histories, you have the one particular history receives the probability 1, and others receive probabilities 0. Okay, so you have like a set of sort of mutually exclusive possibilities within a particular framework, within a particular history. Okay, and here's an interesting quotation from Griffiths, which is that the sample space, in other words, the set of elementary histories, represented mathematically by an appropriate projective decomposition of the history identity, is a collection of mutually exclusive possibilities, one and only one of which actually occurs. So it seems as if, even though Griffiths actually doesn't elaborate on this any further, at least I was unable to find any further explanation. It seems to me that he's kind of like pointing towards the possibility of some form of hidden variables or something like that, that out of these histories, even though they may, several histories may possess non-zero probabilities, actually only one occurs. I can only speculate that this probably comes from the sort of quantum logic intuition background, because of course if you quantum logically take all the histories and you take the disjunction of all histories, either this or that or that or that, then the disjunction is true, okay, because the disjunction is equal the identity operator. So perhaps that's the reason. And on the other hand, Griffiths doesn't want to interpret these alternative histories within a particular framework as if they sort of related to separate universes. So he clearly spells out his sort of his suspicion towards any sort of many worlds interpretation. But I think it's most probably too quick. So, like I said, maybe hidden variables. But in spite of his reservations, I think that we can consider the possibility of, again, applying the many worlds approach to this fine-grained distinction between histories. So here is sort of like my general sort of proposal. You start with this multiverse, which first you have to separate into frameworks, okay? Each framework represents some sub-world, so to speak, or it's better to say that each framework actually represents a set of worlds, okay? And this set of worlds are further distinguished into sets according to the histories, okay? So each history represents a particular sort of like a more fine-grained world. That would be sort of my take. So let me now give you an example, a very simple example. This is a well-known Stern-Gerlach apparatus. You take 3 moments of time, t0, t1, t2. At t0, the wave function is like here omega. then at T1 omega prime, and then of course it splits into, you have two wave functions, omega plus, omega minus. The dynamics is very, very well known. If you start with a system which has its spin z spin up, and it starts with the wave function omega, then of course it will be transformed according to the rules as written here, and the same with the minus. And of course we assume that the initial state is a superposition, so it's the state in which the spin, which the spin of the particle is well defined in the x direction, which is a superposition of z plus and z minus. Now we can write down two families of histories, but of course out of many. There's an infinite number of histories you can write down. You can do it according to the principle of liberty, but we will write down two families. Now one is kind of like familiar. One is you start with the initial state psi 0, the superposition. In the moment right before the particle enters the Stern-Gerlach apparatus, it still has this, its spin x in the plus direction, in the up direction, and then it kind of splits two histories. One history is it goes up, the other history it goes down. That's a well-known story, okay? But it turns out there's another story, and it's equally good. The other story is that the kind of like the splitting, speaking figuratively, occurs even before the particle enters the Stern-Gerlach apparatus, and it's perfectly consistent. You already consider the upper sort of the upper root in which the particle, even before with the wave function omega prime, has spin up in the z direction and has spin down in the z direction, and it just continues along these two paths that I presented on the previous slide. And again, this family is perfectly acceptable. So you may say, like in the first family, or world, or the set of worlds, let's put it that way, in the first set of worlds, the situation is as follows. You have at T1, the x spin of the particle equals plus, or up. And then this is, if you want to calculate probabilities, of course, the dynamics is such that the probabilities of the histories are one half of one, one half of the other. So the probability that the z spin at T2 will equal plus with, of course, 1/2, and will be the probability that will equal minus will be also 1/2. But in F2, like I said, already at this time before the particle enters the Stern-Gerlach apparatus, already you can talk about probabilities. You can say that the probability of z spin up is 1/2, the z spin down is 1/2. And moreover, you can also consider conditional probability, and conditionally on the result that is the result. I mean, I'm talking about sort of microscopic measurement here. We are not talking about macroscopic things, but sort of let's use this terminology. So conditionally on the z spin being equal up, being equal plus after leaving the Stern-Gerlach apparatus, the condition on that, the state before entering the apparatus is also z plus, okay? And the same with z minus. So it's almost as if we are just like, you know, getting rid of the notion of collapse, which is kind of, you know, everything is with conditional probabilities and selecting appropriate histories. You don't use any conditional. Okay, I'm getting to the end. Okay, so here are these words that these worlds that kind of like can be considered here, and the first two correspond to the first framework, the second two correspond to the second framework. Okay, so all these words can be considered here. According to the many word analysis of this case, you have just simply the unitary history. That's the only history that's acceptable according to the many words. And then, of course, we interpret the superposition at the end of this whole process as considering as describing two alternative possible worlds. Okay, so I think that this kind of narrows down this varieties, the varieties of possible words that are present in the consistent history. So consistent histories, in my interpretation of this interpretation, would introduce much more possible words in order to describe alternative, sort of alternative but very well connected realities. The final thing that I wanted to say is about the measurement problem. I just very briefly run through it. Everybody knows what the measurement problem is, how to interpret the existence of objective, of well-defined outcomes of experiments. Now, the solution that is proposed by Robert Griffiths, among others, is basically that because there is an acceptable, admissible framework, family of histories, which consists of states with well-defined values of the measured parameter, well-defined outcomes, therefore, the problem is solved, okay? Now, to that, people like Okon and Sudarsky in their paper 2014, they said, no, that's not enough. Because there are some alternative frameworks in which there's no outcome well-defined. So what are you going to do with these alternative words? So I think that the bone of contention between these two approaches is that they apply two different standards of scientific explanation, okay? And maybe I will talk in detail about this in the discussion or maybe later on. But anyway, I think that the consistent histories approach applies a relaxed notion of explanation, of what it is to explain. To explain some occurrence is to say that it does not contradict any existing laws. Whereas to explain in the stronger sense is to say that you explain an occurrence if it follows logically from the applicable laws and some initial conditions, okay? So this standard of explanation is not achievable in the consistent histories approach, whereas it may be achievable in the many words interpretation. So that's another sort of big distinction between these two interpretations. So thank you very much.
Thank you, Tomasz. That's a very nice review of the consistent histories approach. But you didn't mention the Dowker-Kent objection, and I think people ought to know about it, because it seems to me it's entirely relevant. And that objection says that fix a history up to some time, fix the quantum state, fix even the dynamics, and you can continue and extend that history with respect to a continuum infinity of different history spaces. So that would suggest that you can never know what history space you're in, even given everything there is to know up to some time and the quantum state and the dynamics. And that many people took to be extremely damaging to the approach. I just wonder what you have to say about it.
Well, I can only agree. I mean, that's definitely that's one of the weakest points of this interpretation. This incredible multiplication of possible continuations of histories, which is that's underdetermination, even underdetermination, according to which. But again, I mean, I don't know. I mean, maybe within this framework of possible, I mean, you can just say that this corresponds to an incredible number of alternative worlds, of which, I mean, you select the one that suits best your purposes or something like that. Again, back to pragmatism. I know. It's not a satisfactory answer. But I don't have any satisfactory answer to that, unfortunately. Thank you.
Thank you. I'm interested in the way you describe the many worlds framework inside the consistent histories, because of course there's another way that people do, which kind of follows the Gellman and Hartle tradition, which would say, well, even in the many worlds framework, we want to use non-trivial consistent histories because we want to say what decoherence theory gives us as a history space. It gives us as a history space quite robustly and in ways that are resilient against the Dowker-Kent objection. Mm-hmm. But it gives it to us approximately and emergently, and so we need to tolerate fuzz in a way that doesn't look attractive if we have a sort of fundamental notion of history in the consistent history. Mm-hmm. Okay.
Yeah, I thank you. I didn't mention decoherence in my talk. I should have probably. I noticed, and again, I probably would have to delve much deeper into what Robert Griffiths wrote about that. But I noticed that his approach to decoherence is a little bit like, I mean, you know, it's kind of like half-hearted, or should I say? Yeah. He's the only thing that he stresses is that decoherence can change a consistent inconsistent into consistent, and that's always so. He doesn't even address the issue that decoherence can really select out of the many histories the one that really sort of so it should be taken into account most probably. So like I said, I focused on the presentation by Robert Griffiths, so he's kind of like a little bit put that aside, but that's of course an important thing to take into account.
Thank you.
I spent many hours trying to understand consistent histories and talk to people who invented them, Griffiths. And I had always the most important question, probability of what? I never understood it. If it's probability of measurement to perform, then Aronov, Berger, Leibovich did it at 64 before. And but then kind of said, no, it's more than this. And I never understood what it is. Do you have a feeling what it is?
Well, I definitely spend much less time thinking about the consistent history approach, so I don't know if I have anything groundbreaking to say here other than some form of objective probability. I mean, okay, let me try to turn the tables here. But if we talk about probabilities in the many worlds interpretation, then again, from what I have learned in this during this workshop, is that there are some approaches to this that take this as an objective feature of the world, like you know, representing things like speaking figuratively, how thick the branches, particular branches are, how big they are. Okay, so why can't we sort of approach? Why can't we apply the same sort of analysis to the consistent histories? That they basically represent these probabilities represent some objective features of these alternative worlds consisting of particular histories. Some of these histories are more essential or real, and some are less real. That's one. But then there's this problem. Yeah. I mean, okay, that's probably enough being said. So that would be my answer. Just try to go in the direction of objective probabilities.
Thank you. Just they're all real in the same way, and some of them exist more or less. That's what I believe, the measure of existence. And I don't want to call it probability. And this is why I ask what's probability is. Okay, but I think